Hello, welcome to this lecture series on quantum chemistry. Today I am going to start the next type of motion called rotational motion. So far we have discussed translational motion and vibrational motion. From this lecture onwards I am going to discuss rotational motion. So rotational motion. Okay, in rotational motion let me start with the particle on a ring system, then we'll discuss particle on a sphere, then I'll discuss about rigid rotor. Okay, so under rotational motion I'm going to discuss particle on a ring, with a constant radius, particle on a ring of fixed radius r. Then I'm going to discuss particle on a sphere of fixed radius r. Then I'm going to discuss about rigid rotor, and very specifically I'm going to assume a diatomic molecule as rigid rotor. Okay, so these are the systems we are going to discuss. So first let me start with the particle on a ring of fixed radius r. Okay. Particle on a ring of fixed radius. Okay, so radius is constant, that's the meaning. Now before going to apply the quantum mechanical approach, let me first discuss the classical approach, then we'll see what are the drawbacks in classical approach, then what is the need for quantum approach, that we'll discuss. Okay, then I'll start quantum mechanical approach of particle on a ring of fixed radius. Okay, yeah, so classical approach. Classically, if a particle is rotating or moving on a ring of fixed radius, say for example a particle is moving on a ring, assume that a particle having mass m and it is moving in a fixed radius on a ring of fixed radius r. Okay, so where radius is r. Okay, and you know very well when particle rotate right on the ring, when the particle is moving on a ring of constant radius, okay, depending upon the velocity, the particle will have angular momentum. Okay, so you'll get angular momentum, right? Angular momentum is a vector. Okay, angular momentum is a vector, so you'll get angular momentum at the center. Okay, so for the particle moving around this center point, angular momentum will appear at the center, right? It is called body space fixed coordinate system. Okay, let us not go into that. It's a very simple one to handle. Okay, now what is the energy of the particle? Okay, you know very well total energy equal to kinetic energy plus potential energy. Let us assume that there is no external force acting on the particle. Okay, let us assume assumption. I am going to assume that no external force acting on the particle. No external force acting on the particle. Therefore r, that is radius, r remains constant. Not only r, potential energy, okay, which actually depends on r, right? In this case potential energy is also constant, right? Potential energy is also constant in this, because r is constant, so potential energy also constant. Yeah, And since potential energy is constant, we can assume that potential energy, right, as 0 for our convenience. Okay, so this is the assumption you should keep in mind, right? So I can write this as, what is kinetic energy? Kinetic energy is half mv square. Let us first write linear velocity, kinetic energy in terms of linear velocity. Then since it is particle is moving on a ring, we can change this linear velocity into angular velocity, and potential energy is assumed to be 0 in this case. Therefore the total energy is actually rotational kinetic energy, because potential energy is 0, so total energy is nothing but rotational kinetic energy. Okay, and you know very well linear velocity v, let me write here, linear velocity v is nothing but r into omega, where omega is the angular velocity. So if I replace v square, I'll get r square omega square. So this is rotational kinetic energy in terms of angular velocity. Okay, and you know very well m into r square is moment of inertia. So I equal to m into r square. So if I replace that, I'll get half into I into omega square. Okay, yeah. So this is the rotational kinetic energy of the system. Now I will multiply the numerator and denominator by I. So what we get, I'll multiply the numerator and denominator by I. So I'll get 1 by 2I into I, you'll get I square and omega square. Let me write that as I omega whole square. And you know very well moment of inertia into angular velocity is nothing but angular momentum. Okay, so this is nothing but angular momentum. Let me write in the next page. Therefore the total energy equal to 1 by 2I into L square, where L is equal to I into omega. Moment of inertia into angular velocity will give you angular momentum. So this is the total energy or rotational kinetic energy of the particle by classical method. And according to classical approach, this angular momentum, right, L can take any possible value. L can take any possible value. Okay, so L is actually, L can take continuous value. There is no restriction on this. Since L can take any possible value, okay, therefore E can also take any possible value. Any possible value. That means total energy is continuous. Energy is continuous. Okay, so energy is not quantized, or you can say in the other way, energy is not quantized. So classically the rotational kinetic energy is not quantized, but I'm going to show you that in rigid rotor problem, when you consider diatomic molecule, when diatomic molecule shows rotational spectra, okay, we are going to discuss under rigid rotor problem, we are going to say that rotating diatomic molecule has discrete quantized energies, and it shows rotational spectra. So rotational spectra exist. Since rotational spectra exist, the molecule must possess quantized energy levels. Okay, but classical approach could not explain the quantized nature of the rotational energies. Okay, so that is why we are going to approach we are going to follow the quantum mechanical approach. Okay, so now let me start the quantum mechanical approach of the problem. Yes, quantum mechanical approach. Quantum mechanically we can say, see, let us assume the particle is moving on a ring of constant radius r. let us take this axis as y axis and this as x axis, and let us consider this axis as z axis. Okay, and this is the origin. Now let us assume a particle of mass m. Okay, it is moving on the ring with a constant radius. Here radius is constant. This is r. Okay, so here remember r is constant. Okay, therefore potential energy which depends on r, that is also constant. Okay, for convenience we are going to say that potential energy is 0. For convenience we are going to assume the potential energy is 0. Okay, then what about theta angle? Theta is the angle between the plus z axis and the line joining the origin and the particle. Okay, and here this theta angle is 90 degree here. Theta is 90 degree. As long as the particle restricted to move only in the xy plane, okay, theta angle remains same. So theta angle is also a fixed quantity here, fixed. Okay, let us keep all these things in mind. Now let me start with the time independent Schrodinger equation. Right, the time independent Schrodinger equation for this particle can be given as, since it is moving in xy plane, x variable, y variable, that is x coordinate and y coordinate changes, but z coordinate, since it is perpendicular to z axis, particle is moving perpendicular to z axis. Okay, z coordinate remains same. Right, so only x and y coordinate changes, therefore wave function depends on x coordinate and y coordinate. Right, so you can write this as time independent Schrodinger equation. Let me first write h psi, where psi depends on two coordinate x and y, equal to E into psi x y. First I will write the Schrodinger equation in terms of Cartesian coordinate, then I will change it into spherical polar coordinate. Okay, now what is h here? H is the Hamiltonian. Hamiltonian can be written as minus h bar square by 2 into m, where m is the mass of the particle, into dou square by dou x square plus dou square by dou y square. Since the particle is restricted to move only in the xy plane, okay, we should take only this operator, that is second derivative of x and second derivative of y. You should not include z because z is constant here. Okay, in Cartesian coordinate z is constant. Into potential energy, we have assumed potential energy is 0 for this problem. So potential energy is 0 into psi equal to E into psi. Okay, now I'll bring this h minus h bar square by 2m to the right hand side. This is 0, so I'll bring this to the right hand side. We'll get an expression like this. Yeah, let me write the expression here. So the expression is this. I'll bring this h bar square 2m to the right hand side. So you'll get dou square by dou x square plus dou square by dou y square into psi. Okay, I'll bring this term to the right hand side. I'll get minus 2me by h bar square into psi. Okay, we'll get an expression like this. Now since we have circular symmetry in our case, okay, so we have circular symmetry. I have told you in the last lecture, whenever circular symmetry or spherical symmetry is present, it is better to use spherical polar coordinate compared to what is called the Cartesian coordinate, because the solving Schrodinger equation become easier. Okay, so due to circular symmetry, I am going to change Cartesian coordinates into spherical polar coordinates, that is x, y. Anyway, z is constant here. Z is constant, so you need not take. I am going to convert this into spherical polar coordinate, which is r theta phi. But here r is constant. Theta also is a fixed quantity. See, theta is fixed. Theta value is always 90 degree, whatever may be the position of the particle. Okay, so theta is also constant. Therefore, the only variable is phi. So when you convert Cartesian coordinate into spherical polar coordinates, in Cartesian coordinate we have x and y. In spherical polar coordinate we have only one variable phi. So it is very easy to solve the Schrodinger equation if you use spherical polar coordinate. Okay. So the wave function psi, which originally depends on xy, when I change this into spherical polar coordinate, okay, now the function depends only on phi variable. Whenever wave function depends only on phi variable, we represent the wave function by this symbol phi, big phi. Okay, this big phi represent wave function and small phi represent variables. It's the usual notation for wave function, right? Whenever wave function depends only on phi variable, we write the wave function in terms of big phi. Okay, then we also know this. In the last lecture I gave this expression, dou square by dou x square plus dou square by dou y square equal to, this is in Cartesian coordinate. I'm going to change this operator in spherical polar coordinate. It is equal to 1 by r square into d square by d phi square. Okay, so I'll take this as equation number, let me give some equation number 1. Yeah, I'm going to substitute this in equation number 1. Okay, so that you'll get the Schrodinger equation in spherical polar coordinate. Okay, yeah, let me do it. So what I'm trying to say is that I'll substitute in equation 1. So equation 1 becomes, in the place of this operator I'll put this, so 1 by r square into d square, in the place of psi I'll put phi. Okay, in the place of psi I'll put phi, so d right, here I'll get d square by d phi square. Okay, I replace this operator by this operator, and instead of psi I'll put phi. Okay, equal to minus 2me over h bar square. Instead of psi I'll put phi. Okay, so this is the Schrodinger equation in spherical polar coordinate for particle moving on a ring. Okay, I'll bring this r square to the right hand side, so I can write this as d square phi by d phi square equal to minus 2m r square e over h bar square into phi. Okay, you know very well m into r square is nothing but moment of inertia. Okay, m into r square is moment of inertia. Therefore, the above equation can be written as d square phi by d phi square equal to minus 2ie by h bar square into phi. Then see, 2 is a constant, moment of inertia is a constant for a given particle, E is energy. Let us assume the particle is present in a particular energy level, so E is also a constant, h bar is a constant, so all these things are constant. I'll replace this constant 2ie by h bar square into a new constant, say k square. Okay, so if I do that, if I replace this by k square, I'll get an expression like this. So therefore we'll get d square phi by d phi square equal to minus k square into phi. I'll bring this to the left hand side, so d square phi by d phi square equal to plus k square into phi equal to 0. So this is the second order differential equation we obtain, okay, for the particle on a ring. Now we have to solve this, and it is a very simple system. The solution, I'll give the solution and I'll show you whether the solution is correct or not. See, for this 2 solutions are possible, okay, general solutions. So what are the possible solutions? Possible solution, phi equal to e power I k phi. This is one solution, and another solution is phi equal to e power minus I k phi. Both these solutions are equally valid. How? If you want, you can check it. Do differentiate this 2 times and substitute in this equation. Let us check whether it is correct or not. Say, if I differentiate, I'll take this one. If I differentiate this, I'll get d phi by d phi equal to e power ik and differentiation will give e power ik only. Okay, and the coefficient of phi is ik. I'll multiply this by ik. Then differentiates another time. D square phi by d phi square equal to, you'll get I square k square e power I k phi again. What is I square? I square is minus 1. I square is minus 1. Minus 1 into k square is k square. And what is e power I k phi? That is a wave function we have taken, right? Bring this to the left hand side. We'll get d square phi by d phi square plus k square into phi equal to 0. So we got the same differential equation, okay, by using this solution. So it is clear that this is one of the allowed solution for this differential equation. Similarly, you can also prove that this is also an allowed solution. But you know very well, this represents motion in one direction, this represents motion in another direction. So if particle is moving in clockwise, one equation will be considered as a solution. If particle is moving in the anti-clockwise, another equation should be considered as another solution. So both these solutions are equally valid. Okay, time being, I'll take only one solution because one solution is enough to represent both the moment. Okay, yeah, I'll just discuss. You'll come to know what I'm actually mean here. Okay, yeah. Therefore, the solution for this problem is phi equal to let me introduce some constants, a normalization constant a into e power I k phi, where a is the normalization constant. Okay, I have introduced this for normalization. It's a normalization constant. Right now, okay, how to find the normalization constant value? You just normalize this equation. What is the condition for normalization? Integral. Here the only variable is phi. You know very well the range for phi is 0 to 2 pi. Since it is moving in the xy plane, okay, the angle or the range for phi is 0 to 2 pi. Phi star phi d phi, that should be equal to 1 for the wave function to be normalized. Okay, so integral 0 to 2 pi. I'll keep this one as such. Okay, I'm sorry, I'll keep this one as such. Then one second, yeah. Now I'll substitute this phi here and here. So what is phi? Phi is a into e power I k phi, and phi star is a into you should assume that this a is a real constant, normalization constant. Let us assume that it's a real constant. So imaginary phi star will make it does not interfere on the constant a. Okay, so let the constant a remains as such. Phi star is e power minus I k phi into d phi equal to 1. A into a is a square. Let me take it out. 0 to 2 pi. E power minus I k phi, e power plus I k phi, if you multiply, you will get e power 0. E power 0 is 1. So only that d phi will remain. Okay, what is the integral of d phi? Let me do it here. I'll keep a square as such. Integral of d phi is phi. Upper limit is 2 pi, lower limit is 0. Okay, and therefore a square, I'll put the upper limit here. So in place of phi, I'll put upper limit 2 pi. Lower limit anyway it is 0, so you need not worry about that. So a square into 2 pi equal to 1, or a square equal to 1 by 2 pi, or a is equal to, you will get plus or minus. By convention we take only positive value. Therefore a is equal to 1 by square root of 2 pi. So this is the normalization constant value. Okay, let me substitute this in the place of a. Okay, so that you can find the value of the normalization constant. You'll get the complete solution. Okay, so what is the complete solution? let me write here. So therefore the wave function phi is equal to 1 by square root of 2 pi into e power I into k into phi, right? But right now I didn't apply any boundary condition here. Okay, so now I'm going to apply the boundary condition. What's the boundary condition? Boundary condition is this. Listen, since this particle is moving on a ring, okay, since the particle is moving on a ring, right, suppose assume that, okay, this is the x-axis, this is the y. Suppose assume the particle is here, and this angle, that is angle between positive x-axis and the particle, the line joining the particle, this is phi, right? When the particle goes here, it will take an angle of phi. Suppose if the particle starts from here and goes a full round, that is 360, and again reaches here, if it reaches the same point again, you will get this wave function doesn't change, because wave functions must be single valued, you know very well. Okay, so number of rotations, right, or how many times the particle rotate on the ring, okay, that is not important. And each and every point the value has a fixed wave function, finite wave function. Okay, therefore the wave function phi at a particular angle, the wave function at a particular angle phi should be equal to the wave function at 2 pi plus phi. These two should be same. Okay, therefore what is the wave function formula? Wave function is 1 by square root of 2 pi into e power I k phi, okay, equal to, here we have 1 by square root of 2 pi e power I into 2 pi, that is k, I'll write k later, 2 pi plus phi here, okay, k, right? This you can separate, 1 by root pi, 1 by root 2 pi cancel, so e power I k phi equal to, you can separate this into two part, e power I 2 pi k plus e power I into k phi. You can separate this into multiplication, separate into two part, and this cancel, so e power I into 2 pi k should be equal to 1. Okay, listen, this is Euler's, by applying Euler's theorem you can write this as cos 2 pi k plus I sin 2 pi k should be equal to 1. Okay, this is valid only if Okay, yeah, so this is valid only if k takes value 0, plus or minus 1, plus or minus 2, etc. How? See, if I put k equal to 0, I'll get cos 0. Cos 0 is 1. If I put k equals 0 here, you'll get sin 2 pi. Sin 2 pi is 0. So this is 1. Okay, you'll get 1. Okay. If I put k equal to plus 1, okay, k equal to plus 1, you'll get cos 2 pi. Cos 2 pi is plus 1. Whereas if I put k equal to 1 here, I'll get sin 2 pi. Sin 2 pi is 0. Sin, it will sin all pi values are 0. Sin 0 is 0. Sin all pi values are 0. Therefore, if I put k equal to 0, plus 1, plus 2, plus 3, whatever it is, this part becomes 0. Okay, and this part will get the value of 1. So this equation is valid only if k equal to 0, plus or minus 1, plus or minus 2, etc. Okay, so we made a restriction on the value of k. Now k can take only these values. And listen, the usual notation for k, is actually ml. Okay, you can see in some book they'll put m. I'll use ml because this has some significance in the hydrogen atom problem. Okay, so I'll put ml here. Okay, so I'm replacing the constant k into a new constant ml. So ml equal to 0, plus or minus 1, plus or minus 2, etc. Okay, so ml can take only certain allowed values. Therefore, the wave function can be written as, let me write here, therefore the wave function phi, which depends on the variable phi, equal to 1 by square root of 2 pi into e power I into ml into phi. I into ml into phi. So this is the wave function formula, and here ml can take value 0, plus or minus 1, plus or minus 2, etc. Okay, and what's the expression for energy? You know very well, 2 mu e, 2 I e by h bar square. We have taken this quantity as k square in one place. Okay, in our derivation, we have substituted this as a constant k square. Okay, now k square, I have changed that k into a new constant ml, so I can write this as 2ie by h bar square equal to ml square, or E is equal to h bar square by 2I into ml square. This is the expression for energy, and you know very well h bar is nothing but h by 2 pi. So h bar square is h square by 4 pi square. If I substitute this here, I will get energy which depends only on the quantum number ml equal to h square by 4 into 2, 8. So 8 pi square I into ml square. Okay, so this is the expression for energy for a particle moving on a ring. Here ml takes only these allowed values, 0, plus or minus 1, plus or minus 2, etc. Since ml takes only certain allowed values, energy also, because for a given particle all these things are constant, energy depends only on ml, the quantum number ml. Okay, so here ml is a quantum number. In hydrogen atom problem, we are going to call this as magnetic quantum number. Okay, right now it is just a quantum number. Okay, now depending upon the value of ml, if the particle takes certain allowed values of energy. So keep this point in mind. When particle moves on a ring of constant radius, if the particle is a microscopic particle, then quantum mechanical results suggest that energy cannot be continuous. Energy should be, so E should be discrete or quantized. Energy should be quantized. Okay, I stop here. In the next lecture, I will give you the energy spectrum and the nature of the wave functions. Okay, yeah, thank you for listening.